So we're going to continue on with your equation solving on worksheet 4. 4A is our notes, and then 4B is going to be one of your assignments. There is a new homework checklist out there. Homework check will be due when we test, which will be next Tuesday, and I know last night's homework was a good time. I'm not available today after school, but I can see you tomorrow before or after school if you have any questions. So, these first few questions on worksheet 4 are actually from yesterday, the style of solving from yesterday. So maybe after a few more examples, you'll feel more confident on last night's homework. So we are going to be solving this equation. And it says sine x times cosine x minus 3 cosine x. So I look at the fact that we have multiple types of trig functions in the question, and the first thing I want to look out for is there any factoring in this question? Well, you tell me, are there any common factors we could take out? Cosine, yeah. Well, first I need my pen to start working, and then we'll talk. So if you factor out a cosine from the function, it's still there. There we go. So each term has a common cosine, I agree. If we factor it out in front of the question, you're now left with sine of x minus 3. So that was you factoring, and now you're going to use the zero property that states you can take each factor and set them equal to 0 and solve them. So solving trig equations when we're using our unit circle is a little different. You're just going to get it to the point where you have a trig function solved. So like here, cosine x equals 0, that one's done. We just got to look at the unit circle. And then this one here, sine x minus 3 equals 0. In order to solve that, you'd add the 3 over. So this first one, on your unit circle, it does say all values of x, but for now, just talk to me about one rotation in the unit circle. Where does cosine come out to 0 on your unit circle? At pi over 2 and 3 pi over 2. Very good. And then for sine of x coming out to a 3, remember sine only wiggles between -1 and 1. So this is one of those problems where it doesn't happen, so just cross it off. And then finally, since they want all values of x, what you're going to do, the easiest way to answer this without doing any thinking is just to say pi over 2 plus 2 pi n. And 3 pi over 2 plus 2 pi n. And if you write that down and don't think twice about it, that is totally fine. This is an acceptable answer for your homework, for your tests. However, that's not the simplest version of these solutions. So pi over 2 is right here, and then 3 pi over 2 is right here, and they're just going to keep, like, you'll get a solution, you'll get a solution, you'll get a solution, and it'll keep rotating around that way. How much of a rotation are you doing until you hit your next solution? A pi, yeah, a pi rotation, a half a rotation. So a simpler way to write your answers would be like pi over 2 plus pi n. So that would be like, yeah, that would work. So that's probably what your textbook would have as the answer. If it was a multiple choice standardized test or a textbook answer, they're going to give you the simplest version of it. So it's up to you to realize that you're equivalent to their simple version. Alrighty. This next one, we have cosine squared plus sine plus 1 equals 0. So it's feeling very polynomial-like to me. Unfortunately, I can't work with cosine squareds and sines in the same problem if there's no factoring I can do right now. So you're going to want to trade. Cosine squared is a good trade. That's a Pythagorean trade. What can you trade cosine squared for? Is it 1 minus sine squared? So all the rest of the problem just kind of carries down. And what I'm staring at here is a series of sine squareds, of sines, and then constants. So this is really looking like it's going to be a traditional trinomial looking polynomial. We're going to have to factor this. But your job is to make this as user-friendly as possible. There's no way I want to factor it with the way it currently looks. So first thing I notice is, like, the order is weird, so we'd put the sine squared term first, I think. Oops, I never gave that kid his pass. Josh. 1050. Alright, sine squared, and then we have a, oh, sorry, that was a negative sine squared. And then plus sine of x, and then combining those ones, a plus 2. Now, remember, you don't like to factor when the lead term is a negative, so a little algebra trick would be to either multiply or divide everything by a -1. That swaps everybody's sign. So this is now positive sine x minus sign, sorry, positive sign squared x minus sign minus 2 equals 0. All right, little aside here. Talk about his cousin. This is the cousin to this. So instead of using sine, what if we used x? So that's like a little baby algebra problem. And if I went to factor that one, I would have, let's see, x minus 2 times x plus 1. So now you're going to back up and go back to your trig. Same factoring pattern, but instead of x's, you're going to use sines. So sine times sine in the first terms. And then we're going to use a minus 2 and a plus 1. All right, we're ready to solve. So using your 0 property, you're going to set each one of these factors equal to 0. So this first one, x sine of x minus 2 equals 0, and then this one will be sine of x plus 1 equals 0. And I think I'd claim that this one is going to be that gibberish one where you don't have to solve it because sine is not going to be 2. But talk to me here. When does your sine function come out to a negative 1? Just on one rotation for now. At 3 pi over 2. So the way to fix that for all solutions is just to slap a plus 2 pi n on the end. That just means you're going to keep rotating a full rotation to get there again and again and again. So that's a really typical question of what you could see on a test next week. You're going to have to know to trade out the Pythagorean, and then you're going to have to manipulate essentially a polynomial looking function so you can factor it, and then you got to solve the factors. This is a very difficult concept for pre-calc kids, so you're gonna probably want to practice those questions at length. So when they show up on these worksheets that you're going to be assigned over the next few days, like, don't just copy the answer and move along. Like, really concentrate on how to get that answer. And I know some of you are going to skip this red step over here. Maybe just don't skip it yet. Maybe you're not ready yet. Okay, so there's a little warning on this question where it says graph to check your solutions. What we're going to find out is sometimes we manipulate the equation and we create extraneous solutions. So it comes back to this idea. When you guys would solve, like, I'm just making up this problem. I don't even know if this one works out, but when you guys used to solve this question in Algebra 2 or even in PreCalc, we'd have you square both sides, right? And then this one was easy. This one you had to FOIL out. You ended up with a quadratic polynomial. Sometimes when you do those problems, you create extra solutions that don't actually work when you plug them back in. Remember the extraneous solution idea? You'd solve it, you'd get x equals this and this, and then you'd have to cross off one of them sometimes. That happens in algebra, particularly when you square the functions. We're not going to do that in this first example, but in the next one you're going to see what happens. And it's really hard to check solutions algebraically when you're working with trig. So rather than checking them algebraically, we're just going to check them by graphing because it's easier. All right, number 3. Tangent squared secant. Can't have it. So I need to trade somebody out. So an obvious trade for us is to look for any Pythagorean trades. I'm thinking tangent squared trades for something. What is it? This is the one I always forget. Is it secant? Is it plus 1, 1 minus? This is the one I always screw up. What is it? Secant squared minus 1. Okay. And then the rest of that equation gets written down. So I'm kind of looking through the equation. We've got a secant squared, a secant. We have some constants. So this is just like that last question where it's like a polynomial. We're going to have to factor it. So in pretty factoring order, standard form order, secant squared comes first, and then you're going to have a plus secant. And then when you combine the -1 and the -1, you have a -2. So I'm going to take a little side problem over here. The cousin to that question would just be x squared plus x minus 2. So instead of using secants, I'm going to just use x. And when we factor that baby question, you got x plus 2 times x minus 1 as your factors. So now I'm going to go back to the trig. And I'm going to use that same factoring pattern, except with secants instead of x's. So secant plus 2 and secant minus 1. All right, we're ready to solve. So if you were to set each of your factors equal to 0, now don't get excited about crossing this one off. I almost made a mistake first hour. I went like, oh, the plus 2, gonna be gone. Except I didn't read very carefully. This is the secant function. So we're not ready to cross this one off yet. When you set this one equal to 0, let's talk about what we have here, guys. You're going to subtract 2. But you're not going to see secant on the unit circle. What do you see on the unit circle? Cosine. So what you can do, if you have an equation like this, there's nothing wrong with flipping it upside down. So instead of 1 over secant, let's just call that cosine. And then instead of negative 2 over 1, you're flipping that. So now it's negative 1 over 2. Same thing's going to happen over here. Instead of saying it's the secant equals 1, you're going to flip that upside down. It's pretty boring though. It becomes cosine is 1. So talk to me about all the places on the unit circle between 0 and 2 pi. And we haven't made a big deal about this, guys, but did you notice that 2 pi has a parenthesis on it? So you don't actually count the 2 pi if it's part of your solution set. You don't get to count it because they're going to stop your domain at before 2 pi. So where on your unit circle do you get a cosine in one rotation of negative 1/2? 2 pi over 3 and 4 pi over 3? Okay. And where is cosine equaling a 1? At 0. Now, why can I not count 2 pi? Because this interval here had a parenthesis, so it's not inclusive on the endpoint. You can't include 2 pi. So I just found 1, 2, 3 solutions. I'm going to borrow Hofbauer's picture that she put up here. There's no label on here, but this is 0, and this is 2 pi. Oops, 2 pi. And if they're trying to figure out where this equation equals 0, they're trying to figure out how many times it touches the x-axis between 0 and 2 pi, not including 2 pi. So there's an intercept right here at 0. There's an intercept here, which I'm guessing is 2 pi over 3. And then there's an intercept right here, which I'm guessing is 4 pi over 3. But again, I'm not going to count that last one because they don't want to count 2 pi in my solution set. So 1, 2, 3 solutions from the graph, 1, 2, 3 solutions we found. That means you get to keep all your solutions. That was a hoot. Let's see what else we can do. Oh my goodness. I got a 1. I got a cosine. I got a square root of 3 sine. Those things don't go together. I can't do any obvious trading right now because none of them are squared, so Pythagoreans won't work. So does anyone have a brilliant idea? For what? Because it's not squared, so you can't, huh? So that's the issue we're running into. Nothing's squared, so you don't have any Pythagorean trades. So what if I told you that you need to create a Pythagorean trade? This is something that kids don't think about too much, but what did you do on this question to get going? You squared both sides. So that's a thing. You can do that. Let's do it over here. I'm going to square both sides. Now, this left side, a little more complicated than it appears. It's 1 plus cosine times another 1 plus cosine, so keep that in mind. Got to FOIL that out. On the right side, if you're squaring the square root of 3 and you're squaring the sine, you just square them separately and write them next to each other as a multiplication problem. So squaring the square root of 3 is just a 3. And then sine squared will be your next part of the term. All right, time to distribute. You've got 1 times 1, 1. You're going to have 1 cosine plus another cosine on the outside-inside arch here, so you have 2 cosines. And then cosine times another cosine will be a plus cosine squared. Okay. Well, it's looking a little better because I do at least have some squared things. So we're going to do a Pythagorean trade. It's up to you as to who you trade. However, there's a really easy way to move forward. There's more cosines than anything else in this question, so let's keep the cosines and let's trade out that sine squared. What can you trade sine squared out for? Yeah, that thing, huh? 1 minus cosine squared. So this right here becomes 1 minus cosine squared. But it still has a 3 in front of it. And then all the rest of this equation gets carried down. I should have warned you, this question is going to take you through your margin of your paper. We're not even close to done yet. So start writing sideways. All right, here we go. So definitely have what's going to be a polynomial. It's going to be a quadratic looking thing where we have to factor it. It is not even close to the right form though. Let's distribute that 3. And then we're going to have to move some things around so this side says equals 0. So definitely going to be a factoring question. Move everything to the left side. I'm going to subtract this 3 over. I'm going to add the 3 cosine squareds over. I'm going to try to write them where they belong, though, at least underneath their proper terms. Now, I'm going to do that thing that kids don't like. I'm going to manipulate the equation in my head so I don't have to rewrite it again because I'm running out of room. So I want it written down in standard form order. So the term that we're going to write down first is the cosine squared term. So you have 1 cosine squared plus 3 cosine squared. This is really 4 cosine squareds. You have a plus 2 cosine. And then 1 plus negative 3, or 1 minus 3 is minus 2. Finally, we have a quadratic looking thing. So I'm going to take a detour over to Algebra 2 for a moment. This is the cousin to 4x squared plus 2x minus 2. Think lazy smart here, guys. I want to factor this, but before I look at factoring, what should I do? You should divide everything by a 2. Because it's a number and not a variable or a function, you can actually divide it out of the problem because it's an equation. So new problem is 2x squared minus x minus 1. We got that. Go ahead and factor that for me. That would be, what, a 2x plus 1 times an x minus 1. And now we're going to route back to trig. So be inspired by that question. This blue thing is now going to factor looking like this red thing, but we're going to use cosines instead of x's. So this becomes 2 cosine x plus 1 and cosine minus 1. Woo! Okay, what did I do?
How did the plus 2x go to a minus x?
Oh, dang it. That sure isn't right. Alright, back up. That's a plus. Which means I gotta change a lot of stuff. Okay, so this has to be a minus 1. This is a plus 1. Good call. That would have been really bad later. Which means this is different. Y'all are so polite. Trying not to interrupt my horrible math. Now let's solve it. Good catch. Just edit. Nah, I give up on editing. Alright, so we have 2 cosine x minus 1 equals 0. Gotta solve that. And then cosine plus 1 equals 0. Gotta solve that. 4,000 pages later, we'll almost get our answer, and then you're going to get to see something fun happen at the end too. Alright, so here you have cosine. If you added 1 and divided by 2, they want to know where cosine is equal to 1/2. And then this one is cosine equal to negative 1. Whew. Alright. So they want answers between 0 and 2 pi. Goodness, that's wonderful. Where's cosine 1/2? Look at your unit circle, please. Is it pi over 3? And 5 pi over 3? And where's cosine negative 1? Hi. Oh, thanks. Do we even know where to go? You probably don't even know. That's my favorite thing when you nice, sweet children get a detention and you're like, I don't know where to go. Okay. All right, cosine x. Oh, that was on recording. My bad. Cosine x equals -1. Where was that? 3 pi over 2? No. No. Silly Abruzzo. Pi. Like I said, pi. All right. So, 1, 2, 3 answers. And remember at the beginning of the question it said, you better graph this to check. Now, if I ever wrote that message to you on a test, you better graph it to check, just in case. There's one of these that actually doesn't work. So, if you were to graph this on your calculator, and you don't, for the sake of time, let's skip this step. You would put, you know, 1 plus, the original, 1 plus cosine x into y1, and then you'd put square root of 3 sine x into y2, and then it looks horrendous, but you're going to set your window to 0 to 2 pi, and you're going to see that there's only 2 places where they intersect. So you're going to use that intersect feature to try to figure out which one is not the winner, and it turns out 5 pi over 3 is an extraneous solution that popped up. So just like in algebra, when you square both sides of the equation, you got to be careful because sometimes just random answers will pop up in your math that don't actually work for the question. So as opposed to plugging in 5 pi over 3 into the trig, which is horrendous, I just suggest you graph it. So that was fun. Sorry. All right, on your calculator. Yeah, we got time to do this. So make sure you're in radian mode. Radian mode. And I would like you to type the left side into y1, so just sine x into y1, and then type -0.792 into y2. So, now it did say in the problem that they wanted your all solutions between 0 and 2 pi. So go ahead and set up your x's to be that. So type 0 into y or x min, and then 2 pi into x max, and it'll change it to the decimal. For your max and min, I mean, if you think about the graph here, guys, we really don't need to go beyond too far, -1 and 1. So I'm just going to go -2 to 2. I think at some point in my math, I did zoom trig, so it for the x scale, which it's counting by, it probably adjusted it to, well, at one point, isn't that half pi? So I think it did pi over 2, like automatically from me hitting zoom trig. If you guys hit zoom trig right now, it will adjust a couple of things, and it's going to look fine. You can do that. You could type pi over 2 right here if you want it to count by a certain amount, which would be very smart since we're going to be looking at the graph. So mine is already there, but pi over 2. And then hit graph. So there's sine, and there's that -0.7 whatever it was. So I can see very clearly in this domain that there's 2 intersection points. I need you guys to find each of them. So we're going to go to second trace, intersect, and then when you hit enter the first 2 times, it doesn't matter where you're at, but when you hit enter the 3rd time, it's going to default to the closest intersection point. So if you want to go somewhere else, you either have to scroll over, or you could type in a guess, but remember you're in radians, so like your guesses are going to be like pi, and pi over 2, and 3 pi over 2, so keep that in mind. I just scroll. So that first intersection point is 3.958, write that down, so I'm going to forget that. And then we're going to do that all over again. But this time, when you hit enter the 3rd time, before you hit enter the 3rd time, you either need to get over there, or you need to pop over there by guessing it. So you need to write down 5.466. Oh, I think they wanted more decimal points than that. I apologize. Just whatever you wrote down is good. All right, so now I'm going to do a really horrible rendition of that graph on my paper. So we have the sine function. Yeah, totally. And obviously we know it backs up to. And then you have this -0.7 whatever number here. And you guys just found these 2 ordered pair, or these 2 intersection points. which I did not write down. It's your moment. What are these numbers? What was it? I'm sorry. 3. Thank you. And that guy is... Okay. So come back to the algebra component for me. If this was on a piece of paper, sine of x equals negative 0.792. This is actually something you guys used to do in geometry. When you had to solve for x and it was trapped in a sine function, what did you do? You applied the inverse sine. So now that we're big kids and we got lots of knowledge about inverse sine, what happens on your calculator when you type inverse sine of negative 0.792? Negative 0.8 something.
Negative
0.69. Okay. So that's what my calculator gives me. But why is that not one of my solutions? Because they snuck in this interval right here. It says only between 0 and 2 pi. Is negative 0.8 something between 0 and 2 pi? Nah. So why is my calculator giving me that number then? Well, that goes back to our last lesson on inverse sine. Where is inverse sine defined? Quadrants 4 and 1, right? Only here and here. So your calculator, when you apply the inverse sine to negative 0.79 whatever, it's giving you this guy down here in quadrant 4. But that's because that's how the calculator is set up. It thinks inverse sine is only defined, which it is, from negative pi over 2 to pi over 2. So that's the one it's going to give you, but that's not the one that we were looking for because it wasn't in our domain interval. So this part's going to get a little confusing. If this was on a test, here's what I would expect you to do. For all solutions, all I need you guys to do is just write 3.9585 plus 2 pi n, because this is sine, so it rotates every 2 pi n. And then 5.4663 plus 2 pi n. So if this was a test, that's all I would expect you to do. But I just want to take a little moment to look at this graph for a minute. This is sine, right? So this is 0, this mark here is pi, this mark here is 2 pi. We just decided that this was the one our calculator gave us, so this number right here is negative 0.8, no, negative 0.8169. So how are these all related to each other? Because I have a feeling that this number right here that I can't really see on my calculator right now because of the window is directly related. These two are related to these two somehow. Well, guys, what's the symmetry of this graph? What's the rotation? When does it repeat? What's the period? Every 2 pi, right? So this number here is associated with this number here. Guys, what is negative 0.8169 plus 2 pi? It better be that. It is. So you can see the repetition in the periods here on the graph. The problem with using your calculator is it gives you things like that. So if you're trying to get like a nice looking answer, it's a rough sell. These are not nice looking answers. All right, I don't really want to talk about that anymore. I know that weird like symmetry thing is confusing. On a test, I would just ask that you guys know how to find the intersection and that you know to slap a plus 2 pi n on the end for all rotations. All right, ooh. On your calculator, please. Actually, you know what? Time? I've got time for this. If we had time, though, what you would have done is you would have graphed this into y1. You would have graphed this into y2. And you would have had a weird squiggly thing and then a line. And this problem is a hoot because you would have found 4 solutions where they intersected. And you would have written down all 4 of them. Okay. So on your homework, I think we limited you to problems that only had a few intersections because these are kind of tedious. Let's look at this one though, guys. On your calculator, please. Could you graph me a tangent into y1, tangent of x, and then the line y equals 6 into y2? Oh man, clear. Now, let's talk about tangent for a moment. What's the period of tangent? It's just pi, right? Tangent repeats every pi. So it does say for all solutions. I don't really think we need to look too much into the tangent graph. I think we can just set up our domain as 0 to pi. So it goes 0 to pi this time. I'm still going to count by half pi's, so that way when I see a tick mark, I know it means half pi. But your y's, remember we're trying to see where it crosses 6. So I'm going to need your y's to be outside of 6. So it could be like 4 and 8. It doesn't even have to be symmetrical, guys. I don't care. You could have hit zoom trig at this point and you would have seen a beautiful picture. It just might not be appropriate for the problem. Okay. So I can see there's an intersection point. So you're going to find it. Spoiler alert, I have it. It's 1.4056. So the direction said find all solutions. Now be careful here, guys. If this is tangent, tangent's going to repeat how often? Pi. So instead of putting 2 pi n, you guys are just going to do plus pi n on the end of that. If you ever hit zoom trig, which is zoom 7, you're going to see some beautiful trig curves. But like I said, I don't necessarily know we needed that entire domain to see what was going on. Alright. Oops, I didn't write that down in the right spot. What did we just get? 1.4056, and then it was plus pi n for all rotations. There we go. Alright, this is the last thing I have to teach you guys, and it's a doozy, so hang with me. We have a complicated trig question that I'm going to ask you to solve. So inside of the sine function, every problem up until right now has had x, like nothing else. But it doesn't have to be just x inside of the trig function. It could be 2x, or on our homework we're going to see 3x, 3 theta. So the problem is you guys don't know your multiple angle identities at all to do any trading, so you're stuck solving this one using another method. We've done this before. It's called U-Substitution. So we're going to change the problem so it's simpler, and then we're going to come back and change it again. So we're going to start by saying, I don't know what sine of 2x is, but if I pretend that this is really a u, then I can move forward. So kind of in my brain, on my paper, I'm going to write down somewhere that u is equal to 2x. I'm going to have to come back to that in a moment. So if I was to look at that question, so the sine of some mystery angle u is negative square root of 3 over 2. I know normally we find the one rotation thing first and then we talk about all rotations, which we're kind of going to do that. I want you to look at your unit circle and tell me where is the sine function going to come out to negative square root of 3 over 2. At 5 pi over 3 and 4 pi over 3. Good. So here's what we're going to have to do. Because of the U substitution, you actually have to do this question first. So you're going to look at the unit circle and then slap the rotations on the end. What's the rotation for sine again? You're going to be adding 2 pi n. But wait, u isn't even a thing. What is u? It's 2x. So you got to scribble that out and say that this really says 2x equals all this business. All right. And we still have a problem because I don't care what 2x is, I care what x is. So look at this question, guys. I know it's complicated looking, but how would you solve for x? You would divide everything by a 2. Now you can write that as multiplying by a 1/2 in front, like this. Or if you don't like that, because I don't like that, I literally go and divide by 2. If it already has a denominator, I just sneak an extra 2 in the denominator like that. So ladies and gentlemen, what do you get on that top equation for x? This guy, when you simplify it, you get x equals, what's going on here? 5 pi... I feel like I did something wrong. Are we good? No, we're okay? Okay. So that's 5 pi over 6 plus, and then 2 pi n over 2. The 2's are going to cancel, so you got plus pi n. All right, so there's one solution. Now you got to do that same thing for the other equation. So either multiply everything by a 1/2, or you can think of it as sneaking in a divide by 2 on all of them. Whew. So this guy becomes x equals, so 4 pi over 6 reduces to 2 pi over 3. And then here the 2's cancel again, so plus pi n. So if all they want is a representation for all solutions, that's your answer. But that's not all they wanted. Remember that very first question? It said, give me all your solutions between 0 and 2 pi. Now you're going to go back and you're going to do this question. So here's what's going on, guys. You're going to start plugging in integers starting at 0 for the n. So 5 pi over 6 plus 0 pi's is easy. That's just 5 pi over 6. But what if you add one rotation of pi to that? So what is 5 pi over 6 plus 1 pi? Well, guys, if you can't do the fraction work in your head, that's okay. On your calculator, you're going to type 5, 6 plus 1, and then you're going to math enter that. So what's 5, 6 plus 1? 11 pi over 6. And then maybe you keep going. But what happens when you take 11 pi over 6 and you add another 1 to that? You get 17 pi over 6. And why am I not going to write that one down? It's not between 0 and 2 pi. Remember, they want you to stop at 2 pi. So these are the only solutions for this first one. How about this next one? So if I plug in 0 to here, I get 2 pi over 3. But if you add a pi to that, so if you're on your calculator, you're just typing 2/3 plus 1, math enter. Calculator not friends are doing 2/3 plus 3/3, so you get 5 pi over 3. And if you add another group of pi, what do you have? 8 pi over 3. Am I going to write that one down? No, that's too big. So these 4 answers are the answers to this question. Wow, good luck following your work on that one. So you start with U-substitution, you go find all solutions, you got to do some weird fraction work. That's all solutions. Then you got to come back and find those very particular solutions they wanted. These are nasty. All right, on the back, there's this worksheet that's going to be assigned to you. You guys are going to be working on, not the ones that are circled, by the way. The ones that are circled are ones that I'm supposed to do for you for practice and notes. But you are going to be assigned numbers 2, 4, 6, and 7. So with that being said, I will not be doing numbers 2, 4, 6, and 7 for you. But I will do number 1. So it's one of these U-substitution questions. So first issue we're going to have here on number 1 is that the cosine function is not isolated yet, so we're going to have to do that. So divide by -8. And then they've got the cosine of 2 theta. If I reduced this fraction, I would have negative square root of 2 over 2. All right, so to kind of keep consistent with like the visualization of our notes from the last time, what I'm going to do first, because it does say they want answers between 0 and 2 pi, that's not where we get to start. We're going to start by doing a U-substitution problem, saying that this is really the cosine of U, and we'll come back and plug that back out in a minute. But when is the cosine coming out to negative square root of 2 over 2? Is it at 3 pi over 4 and 5 pi over 4? Okay. So right now what we're doing is we're going to find all solutions, which means I have to throw a plus 2 pi n here. But here's the problem. I don't care about the u. I care about x or theta or whatever the question is. So now I have to go back and say u is not a thing. U is actually 2 theta. And I need you guys to help me solve for theta. So you can either multiply everything by a 1/2, or you could distribute a 2 to every denominator. That's the same thing. So this top one gives you theta equals 3 pi over 8 plus pi n. And then this bottom one's going to give you, oh boy, 5 pi over 8 plus pi n. So this is great. And if the question says find all solutions, I'd be like, here you go, and then I'd walk away. But what did the question say? It said find solutions between 0 and 2 pi. So now I got to back up and actually answer the question. All right. So if I don't add anything, I start out at 3 pi over 8. But what happens if you add a rotation to that, guys? What's 3 pi over 8 plus 8 pi over 8? 11 pi over 8. Are we still good in the right interval? Yeah. But you're not going to be able to add another 8 to that, right? That'll be too big. So stop. All right, next theta. 5 pi over 8 is the first one. But if you add a pi rotation to that, 5 pi over 8 plus 8 pi over 8 is 13 pi over 8. And if I add another one, I'll be too big. So these are actually the answers to that question. So that was a hoot. Can't wait to do that on a test. Okay, so for your homework, you guys have this. So you have a very short assignment. This is probably graphing calculator questions is my assumption. So I think all of them are actually. And then this is that worksheet that we were just looking at with the U-Substitution business. So if you're struggling with last night's homework, try it again, maybe with some fresh eyes. Hopefully you can muscle through that one. I know this is not easy, guys. These are very hard. These 2 days that we've learned, they're 2 separate sections on your test. There's regular equation solving, which was yesterday, and then there's advanced equation solving, which is this hot mess. And it is a hoot. All right, good luck.